So we've seen a lot of NMR theory, but you really won't be able to be good at NMR until you start seeing some examples. And mostly what you're going to want to be doing is taking a spectrum and getting from it a structure rather than the other way around. So I want to start out in this video by showing you the local magnetic field that's generated when we apply an external field. So the external field here is in blue, represented by H0, and then the electrons are moving in a pattern right above and below in that p orbital, and that's creating, the moving charge here is creating a local magnetic field that in the center of that electron motion is opposing the external field. So inside here, H local opposes H0, and we have significant shielding. But the hydrogens are not in there. The hydrogens are out here, and out here, where the magnetic field vector is returning to the top, the H local is reinforcing the external field. So this is why the hydrogens on an alkene, ethene in this case, are shifted far downfield, where H local is reinforcing the external field, and that was the way I was showing with the vector diagram. When you add those two together, you get an effective magnetic field that's larger than the applied field. And then this shows the same system, but for the aromatic ring, where it has 6 electrons creating a ring current. So we've got the external field, and inside the ring, right, the electrons are flowing around the ring here, creating a induced field that inside the ring is opposing it, heavily shielding, and then outside is reinforcing. So again, we've got the sum of the external field and the local magnetic field adding up to make the effective magnetic field larger than the applied field, the external field here. And so these are heavily de-shielded down around 7 and 8. Here's the diagram for the alkene again, and juxtaposed with the diagram for the alkyne. And remember, the key difference was the alkene aligns itself perpendicular to the external field, which means that the hydrogens lie here in the region where the local magnetic field reinforces the external field, whereas the alkyne, because you've got those 2 pi orbitals perpendicular to each other, allows electrons to circulate around the bond axis, thus lining up parallel to the external field, which means that the local magnetic field here, which opposes the external field, that's where the hydrogen is. So the hydrogen is shielded relative to the alkene, and we see those only at around 2.5, maybe 3 parts per million instead of the 5 to 6 parts per million that we see for the alkene. Right? So the alkynes are not de-shielded the way the alkenes are. They're somewhat de-shielded by the presence of the pi electrons, but then they're re-shielded by being in this region where the local magnetic field opposes instead of reinforcing the external magnetic field. So those are just probably nicer diagrams than the one I was able to draw on the board. So let's take a look at some actual spectra. This spectrum was the second edition of Volhard and Short. It's run on a 90 megahertz instrument, so you'll notice that there are 90 hertz for each part per million. So at 10 part per million, there's 900 total hertz, right? So 1 part per million is 90 hertz, this is 180 hertz, etc. At 450 at 5. Right? So you'll notice that the integration on this is run by just pushing a pen along, and when it starts feeling some of that radio frequency being absorbed, it rises, and then you see this ringing effect where the pen is moving too fast to stop when it hits the baseline. So it kind of goes down to the bottom and then gradually recovers. And here you can see for the larger peak, it goes down to the bottom and then recovers too much and then recovers a little. That's called ringing. You'll see that on the old low resolution spectra that are run with an actual chart recorder with a moving pen as opposed to a computer. Right? So we see here that we've got 2 peaks. If I blow that up a little bit, right, you can see that there are 2 peaks. They're both in that region between 3 and 4 because all of these hydrogens are attached to carbon adjacent to an oxygen. There's a plane of symmetry down the center of the molecule, so these 4 hydrogens on the 2 CH2 groups are magnetically equivalent, which means they don't split each other, and so they show up as a singlet. And then the 3 hydrogens on the methyl group are identical to the 3 hydrogens on the other methyl group. Those 6 hydrogens show up as a singlet. Because these are only close to 1 oxygen and these are closer to 2 oxygens, being close to 2 oxygens moves you a little bit further downfield. So our 4 hydrogen peak is further downfield than our 6 hydrogen peak. And it's a total of 45 millimeters if you measure from here to there in the textbook. It's 70 millimeters if you measure from here to there, right, on the textbook diagram. So 135 millimeters represents the total of 10 hydrogens, which means 13.5 millimeters per hydrogen. And that means that for 4 hydrogen, right, for 45 over 13.5, right, that's about 4. And that's going to be equal to 4 hydrogen integration, and 70 millimeters over the 13.5, right, per hydrogen. That's going to be equal to about 6. So we've got the 4 and the 6 equivalent hydrogens because of this symmetry and the magnetic equivalence. And let me take that back down. So here is the same spectrum, but this time run on a 300 megahertz instrument, right? And you'll see that there's no ringing, right? It's a much cleaner spectrum where the line just ends. And we've got 10 millimeters this time and 15 millimeters, right? So that 25 millimeters is equal to the 10 total hydrogens. That's 2.5 millimeters per hydrogen. 10 millimeters over 2.5 is equal to 4. 15 millimeters over 2.5 is equal to 6. So again, we've got that 6-to-4 ratio of equivalent peaks, but much cleaner on a 300 megahertz instrument. Here's a propanol, right? 1, 2, 3. It's a propanol. It's 2,2-dimethyl 1-propanol. That's carbon 1. The alcohol's on carbon 1, so it's 1 propanol, and there are 2 methyl groups there. So there are 3 identical methyl groups, right? That's going to form a 9 hydrogen integration, and it's about 0.9 part per million. This is one of the patterns you should learn to recognize. When you see a 9 hydrogen integration peak at about 0.9, that's a t-butyl group, always a t-butyl group. And then we have a 2.5 millimeter peak here. That's the alcohol. It's a 1 hydrogen integration. The only way to have a 1 hydrogen integration in this particular molecule, right, is to have the alcohol. And then the CH2 that's attached to the oxygen is down here in this 3 to 4 region, which is where you expect to find it. So in this case, we actually can calibrate to 1 hydrogen at 2.5 millimeter. 5 millimeter over 2.5 means this is worth 2, and 22 millimeter over 2.5 means this is worth 9. So you see the integral line here, and it's a very clean spectrum. 3 singlets. There is no hydrogen on this carbon, so there's no adjacent hydrogen to do any splitting of the methyl group, no adjacent hydrogen to do any splitting of the CH2 group. And remember, since the OH group is exchangeable, it isn't split, and it doesn't do any splitting. This hydrogen is only there some of the time on the NMR time frame. And that peak is variable anywhere between 0.5 and 5. Here it shows up at about 1.8 for the singlet for the hydroxide. So 2,2-dimethyl 1-propanol gives a very clean spectrum with 3 singlets. Here's bromoethane run at a 300 megahertz instrument, so nice clean spectrum. And we've got 3 magnetically equivalent hydrogens in the methyl group adjacent to the 2 hydrogens of the CH2, which are in a different chemical shift, which means they will split the methyl group. The n+1 rule is in effect here, and we've got these 3 hydrogens from the methyl group split into a triplet. This is a terrible tree diagram here. Really, there should be 1 branch per adjacent hydrogen. So this should be split into 2 branches where you get that coincidental overlap that shows that the middle peak is twice the intensity of the outer peaks. And then the CH2 group shifted by bromine, so it's down at about 3.4, right? A little less far than it would be if it were chlorine or oxygen that's shifting it downfield, and split by the 3 adjacent hydrogens of the 3 identical hydrogens of the CH3 group adjacent into a quartet. So we got an upfield triplet and a downfield quartet. That is a pattern that you're going to recognize as an ethyl group. A 3 hydrogen triplet upfield, a 2 hydrogen quartet further downfield is an ethyl group. And in this case, because it's between 3 and 4, it tells you that that ethyl group is adjacent to an electronegative element. If this was not an electronegative element, you might expect to see that quartet, further up. So bromoethane, ethanol would look fairly similar, except that there would be a single hydrogen for the alcohol somewhere, probably around here. Chloroethane would look almost identical, except that this 2-hydrogen quartet would expect to be a little bit further downfield. Usually there's going to be a singlet at 0 for our internal standard, the tetramethylsilane, and you actually saw that present in the previous 2 spectra as well. If we increase to bromopropane, we now have the same 3-hydrogen singlet that we would have for bromoethane, split now by the CH2 in the middle. The CH2 adjacent to the bromine is down there in that 3 to 4 region, but now instead of being split into a quartet, it's split by a CH2 group, not by a CH3, so it's also a triplet. And then the 2 hydrogens in the middle here are split by 5 hydrogens. The CH3 and the CH2 next to the bromine are not magnetically equivalent to one another, but they do split with the same coupling constant of about 7 Hertz. That's a standard alkyl coupling. Because that coupling constant is the same, they still follow the n+1 rule and they match Pascal's triangle. 5 adjacent hydrogens will split into 6 peaks, so we see a sextet here, right? And that sextet is it's split not by 5 magnetically equivalent adjacent hydrogens, but by 5 adjacent hydrogens that split with an identical coupling constant. Right? You'll notice that the peak is not entirely symmetrical. This one leans a little bit towards the downfield side. This one leans a little bit toward the upfield side. They always lean towards what is splitting them. So since the peak that's doing the splitting is further downfield than this one, it leans a little downfield. And since the peak that's doing the splitting of these is further upfield, it leans a little towards the upfield. Just for contrast, here's the same spectrum, but run on the 90 megahertz instrument, and you see how much messier it is. Right? You see that we have now this ringing effect, right? So we don't see nice clean peaks here because of the pen movement. And this sextet is nowhere near as clean, and again, this triplet's not very clean because the pen is doing that kind of ringing. Even with the tetramethylsilane peak, you see that you've got that pen overshoot factor that makes them a little messy. You'll see these lower resolution spectra from time to time, and you'll have to get used to recognizing this as a triplet, even though you've got kind of this mess underneath. Notice it leans upfield. The lean is more pronounced here than it was in the 300 megahertz spectrum run digitally. The lean downfield is more pronounced on this upfield triplet, on the one that's run using an actual scanning pen as opposed to a digitization. Here is a 2-iodo propane. The fact that it's iodine isn't really particularly relevant. You'll notice it's shifted quite far downfield, even though iodine is not electronegative, because a methine hydrogen is typically shifted further downfield than a methylene hydrogen. We've got 6 identical adjacent hydrogens that should be splitting this hydrogen on the carbon with the iodine into a septet, 7 peaks, in the Pascal's triangle ratio of, well, the 2 outer peaks are very small relative to the internal peak, almost lost in the baseline, but it's clearly a septet. There should be 6 branches to this tree with lots of coincidental overlap. And then the 6 hydrogens are split by this one adjacent. These are magnetically equivalent because they reflect into each other, and then these 3 rotate into each other. So you have 6 identical hydrogens showing a 6-hydrogen multiplet, and the coupling constant is the same because the blue hydrogen is splitting the red hydrogen with an identical coupling as the red hydrogens are splitting the blue. So you've got an upfield doublet, 6-hydrogen integration, and a downfield multiplet, 1 hydrogen, in this case a sextet. That is a very distinctive pattern for an isopropyl group. This is isopropyl iodide. So you should recognize that upfield 6-hydrogen doublet and a downfield sextet in this case, because there's no other adjacent hydrogens, right? There's just the iodine. Upfield doublet, downfield sextet. Sometimes it's even more split because there might be a CH2 here, for example, so it would be split by 8 adjacent hydrogens into a nonette. But that pattern, upfield doublet, 6-hydrogen, downfield single hydrogen multiplet, distinctive for an isopropyl group, right? And it follows the 1 to 6, what's Pascal's triangle for the septet? 1, 5, 10, 10, 5, 1 is the sextet. So 1 to 6 to 15 to 20 to 15 to 6 to 1 would be what you would see for the septet. patterns that you'll kind of learn to recognize when you have just two adjacent hydrogens, like in an AB, you'll see a pair of doublets, one probably further downfield than the other. When you have a CH2 next to a CH, right, you'll see a doublet for the one and a triplet for the other. A pair of CH2s adjacent to each other give a pattern of two triplets. The CH3 next to a CH, right, an upfield doublet and a downfield quartet. CH3, CH2, that's your ethyl group, like an upfield triplet and a downfield quartet, typical of an ethyl group. And then this is your isopropyl pattern, where you have an upfield 6-hydrogen doublet and then a downfield septet for the single hydrogen. Isopropyl groups and ethyl groups are very recognizable patterns, but you'll see some other patterns that you'll learn to recognize. And then whatever is attached here can't have any hydrogens on it. So these would be either like an OH group or a benzene ring or something. Very common kind of patterns. But these two, the ethyl group pattern and the isopropyl group pattern, you should really learn to recognize, along with that single hydrogen, or that 9-hydrogen singlet at 0.9 for the t-butyl group. So here's a slightly more complicated one. This is 1,1,2 trichloropropane, right? So 3 carbons, 1, 2, 3. Carbon 1 is the one with 2 chlorines on it. 1, 1, 2 trichloropropane. The CH3 is split into a nice doublet, right, by hydrogen B. 6.8, that's close to 7. That's your kind of normal coupling constant that you see for an alkyl group where you've got free rotation. But then HA is not magnetically equivalent to the CH3 group, which means that hydrogen B is not going to be split by 4 identical coupling constants, right? So it's not going to be split following Pascal's rule, Pascal's triangle, into the n+1 rule into a pentet. It's actually going to be split into a doublet of quartets. It's a much smaller coupling constant because there's not free rotation around this C-C bond with the steric hindrance of the chlorine groups passing by each other. So the A-B coupling is only 3.6 Hertz, quite a bit smaller than the B-C coupling constant of 6.8 Hertz. So each of the peaks of that quartet that you would normally see from the CH3 is split into a doublet. So we got a doublet on the outer, and then the 2 inner peaks are split into doublets, and then a doublet on the outside. Again, this isn't a very good picture, right? You really ought to have 4 branches in your tree, or for 4 adjacent hydrogens, and they're showing the quartet, right, with just 1 branch rather than showing 3 individual branches with the overlap, which is what you would expect to see. So we've got a 1 to 3 to 3 to 1 quartet, followed by peaks 1, 3, 5, and 7 on this 8-peak multiplet, and then we've got a 1 to 3 to 3 to 1 quartet shown by peaks at 2, 4, 6, and 8. It's a doublet of quartets, so that's kind of a non-first order pattern. It's not 4 adjacent magnetically different hydrogens, which would lead to 2 to the 4th or 16 total peaks, but it's also not 4 magnetically equivalent adjacent hydrogens, which means it doesn't follow the n+1 rule, so it's not 5 either. This hydrogen A is split only by hydrogen B. The coupling constant is 3.6 Hertz because A and B split each other with identical coupling, so we've got a downfield 1 hydrogen doublet. And you'll see that's way downfield. That's in the alkene region between 5 and 6 because it's next to 2 electronegative elements, and there's another electronegative element on the adjacent carbon which shifts it even further downfield. So you can't see a peak between 5 and 6 and necessarily say that it's definitely an alkene. More than one electronegative element can have an additive effect. So here's a spectrum that I'm showing the molecular formula for. It's C6H12Cl2O2. The first thing we want to do when we have a spectrum like this, when we have when we're not given a structure or molecular weight, we have the molecular formula, is we want to calculate a degree of unsaturation to see if there's likely to be an alkene, right? There is a peak between 5 and 6. It could be a hydrogen on a carbon-carbon double bond. So we want to find out if there's any unsaturation. A C6 molecule would normally be C 6 times 2 is 12 plus 2 is 14, right? C6H14 would be saturated, CnH2n plus 2. The 2 chlorines are added to the number of hydrogens when we do degrees of unsaturation because they're a 1-for-1 replacement. So C6H14 is what it should be, and C6H14 is what we actually see. 12 hydrogens plus adding 2 for the 2 chlorines So the degree of unsaturation here is 0. This is a saturated compound. There are no pi bonds and there are no rings, right? Which means that the reason this is between 5 and 6 must be because of the extra electronegative elements, not because of the presence of a pi bond, a CC double bond. Right. We see that there are actually only 4 different signals for the 12 hydrogens, and that there are 6 hydrogens that are giving rise to a triplet here. 6 hydrogens is a multiple of 3. It's probably a pair of identical CH3 groups, a pair of methyl groups. And those methyl groups are split into a triplet, which means they're adjacent to 2 hydrogens, right? 3 peaks would mean 2 adjacent hydrogens. So this is probably 2 adjacent CH3 groups next to CH2s, right, which is an ethyl group. And then now I see that there are 4 identical hydrogens that are a quartet down here. Those are CH2 groups, probably identical CH2 groups, split by 3 adjacent hydrogens, most likely a methyl group. So this upfield triplet, downfield quartet pattern is very typical of an ethyl group, right? And in this case, 2 identical ethyl groups. This peak is between 3 and 4, which probably means that that ethyl group is attached to the oxygen. It can't be attached to the chlorine, right, because that would just be chloroethane, which would be a molecule in its own right. So I probably have here ethoxy groups, CH3CH2O, right? And I have 2 of them, and those 2 are identical. So I'm going to open up ChemDraw here. Okay, I'm not going to open up ChemDraw because I have to reinstall it since the license has expired. So never mind. We're not going to do that here. Anyway, so I have 2 identical ethoxy groups. Right? That's using up C6, right? All of the carbon, C4, right? 2 carbons for each ethyl group, and 10 of the hydrogens, right? Because a CH3CH2 group has 5 hydrogens on it. That leaves me with 2 carbons, 2 hydrogens, and both my chlorines, right? I've used the oxygens as part of the ethoxy group. So I've got 2 carbons, 2 hydrogens, and 2 chlorines left in the molecule. Those 2 hydrogens are magnetically different and probably splitting each other because they lean towards each other, and it looks like the coupling constant is identical, right? And it looks like that coupling constant is a little bit different than the coupling constant here, right? This coupling constant should match this coupling constant because these things are splitting each other, but it looks like it's a little bigger than the coupling constant here. What that probably means is these 2 chlorines are, or these 2 hydrogens are on adjacent carbons. So there's a CH and another CH next to each other, right? And that pattern is consistent with 2 CHs, right, adjacent to each other. So I've got 2 identical ethyl groups, probably with an oxygen attached, and then I've got this CH pattern. The way to make the final structure would be to attach the ethoxy group, right? Attach both the ethoxy groups here and attach both the chlorines there. If I attach 1 ethoxy group and 1 chlorine on this side, and 1 ethoxy group and 1 chlorine on this side, I would have a plane of symmetry down the middle, which means these 2 hydrogens should not be magnetically different. So the structure indeed has 2 ethoxy groups attached to the 1 carbon and the 2 chlorines attached to the other carbon, so there's no symmetry between hydrogen A and hydrogen B, right? Those show up as magnetically distinct. They're splitting each other. There's not free rotation, so they're splitting each other with a smaller coupling constant, and then these 2 CH2s reflect into each other, these 2 CH3s reflect into each other. So I have 4 hydrogens that show up as a quartet and 6 hydrogens that show up as a triplet.